Hi everyone, I'm Navjot. I joined the Scalable Solvers team in September, and I'll be presenting my work on sparse tensor decomposition for non-Gaussian data. It's a bunch of words, and I'll try to explain them in the next few slides. It's, so what are tensors? So for the purposes of this talk, tensors are just multi-dimensional arrays of numbers. They generalize the concept of vectors and matrices. So think of numbers arranged in higher dimensions. The dimension of that tensor, I will represent it as modes, and the number of dimension of the tensor, I'll represent it as the order of the tensor. So I have an image or a cartoon to visualize what are tensors. So we have an order zero tensor, which is just a scalar, a number. We have the matrix, which is an order two tensors, and the modes are rows and columns. And I just have a order three tensor, which is numbers arranged in queue. Okay. And where do these occur? Well, they are everywhere. You can formulate the Netflix ratings as a third order tensor where the modes are user, movie, and time. You can formulate gene expression data as another third order tensor where the modes are sample and tissue, and good genes interact with that sample and tissue. You can have the EEG data represented as an order three tensor where the frequency, channel, and time are the modes, and there can be many more. And why do we want to decompose them? Well, as we saw that these can be order n tensors. So the order of the tensor can be n. So they suffer from the curse of dimensionality. So as the order increases, we suffer from memory explosion. So one of the applications is data compression. So what if you want to store this big tensor in a small memory? You would want to compress the tensor while preserving all the important information. One of the applications is compression, the other is data analysis. So once you decompose this tensor, you get some smaller tensors, which can be visualized to do several downstreaming tasks like clustering, classification, and generate actionable insights from those. I have an example of a tensor decomposition of the EEG data, and you can see how it lights up different parts of the brain with different factors. Okay. There are a couple tensor decompositions that I'm going to talk about in this talk. First one is canonical Poisson decomposition, the CP tensor decomposition. So what CP tensor decomposition does is it breaks down the tensor into sum of outer products. So there are R of them in this diagram, where R represents the rank of the tensor. So a tensor of size I cubed, where I is the mode size, is decomposed into matrices of size I by R. So you can see the compression there. Tucker decomposition is a generalization of CP, where we introduce your core tensor, which is also of the same order as your input tensor. Okay, now I'm going to talk about what is sparsity and what is the non-Gaussian in my talk. So if you want to decompose there are only few libraries which do sparse tensor decomposition, and most of them are limited to doing Gaussian decomposition. Whereas the real world tensors, if you see, these are mostly sparse. So majority of the entries on the tensor are missing or zeros. For example, the Netflix ratings will have a lot of missing data, as only a few users will rate a few movies. The gene expression data will largely be zeros, as not all genes will be expressed in all tissues. Also, these entries may be non-Gaussian. So the gene expressions will probably be binary, as they represent only the connections. The Netflix ratings will only be natural numbers, so numbers between 1 to 5 or 0 to 5. Assuming a Gaussian data would mess up the reconstruction, as you might get negative numbers and numbers outside of these ranges. So that's the challenge that we're going to tackle. So I'm going to explain how we do it in just one slide of math. So what we do is we associate a probability distribution to each tensor entry, which is represented as P here, and the theta represent the probability distribution parameters. The X is your reconstructed tensor, and S is the set of tensor decomposition parameters. So once you impose conditional independence on these parameters, you get a loss function via maximum likelihood, which is given in blue. That's what we want to care about. This is a minimization over the tensor decomposition parameters S that we want to solve, where phi is some convex loss that we're going to minimize based on your assumption. It can be Gaussian, Poisson, Bernoulli, depending on the data. Okay. So we have our objective function in the blue on top, and we want to optimize it for a sparse tensor T. And if you try to compute gradients for Gaussian, that is easy because Gaussian loss will preserve the sparsity and you can get gradients easily, and your Hessian as well. Whereas for non-Gaussian, this is not the case. So you need to choose your psi and phi smartly to preserve the sparsity. What we do is we provide a systematic mathematical framework to choose these nonlinearities so that the gradients and Hessian preserve the sparsity and we can compute all of this efficiently. We also provide the software to do that. I'm not going to explain how we do it, but there's like a lot of things that are going on, that how you distribute the tensor entries, and it's irregular because it's sparse, and it's a bunch of communication cost analysis and everything. But what we do is formulate an alternating optimization method, which is implemented in Cyclops library, which does distributed tensor contractions, and be sure that it outperforms most of the existing methods, well, all of them. And since there is no other library that has done this general case, to establish benchmarks, we're going to compare it to Sparse Tensor Decomposition library that only tackle Gaussian loss. And so in this first case, I compare our implementation with Splat, which only does Gaussian CP decomposition. For reference, so I use a synthetic tensor that I just created, which has mode size 1 million and it's order 3. So if you just store it as a dense tensor, it will be 1 million terabytes. So that's the scale of the problem we're looking at. And so we do our algorithm, and I have a plot of one iteration to compare Cyclops and Splat. Cyclops is in blue, Splat is on the right side, and it's a time per iteration. So you can see that Cyclops takes 8 seconds to complete one iteration, whereas a Splat takes more than 14. So that's 1.7 times faster. So we feed Splat at its own game. Then I try my implementation versus the benchmark, which is P Tucker for Gaussian Tucker. So it's Tucker decomposition for least squares. And I try a relatively smaller size tensor because P Tucker wasn't very well optimized, and we are about 60 times faster per iteration. We'd also distributed memory, whereas P Tucker is shared memory. But okay, but we can do more. We can do other losses. So I have one example. I decomposed a tensor with binary data, which is the DBLP data. So it has authors by venues by time. If you store this tensor as dense, which people would do because they want to do Bernoulli, this would be 340 gigabytes of your memory and very slow to decompose it. Whereas I can do 100 iterations in almost no time. And you can see I do an alternating minimization method, where the loss is decreasing per decimal. Yes, that's it for now. So so our code is open source and it's available on GitHub. And this is an ongoing work. So I have a previous publication associated with this work. And we're trying to do more applications with it. So if you know about some, let me know. Thanks.